Well, some of you who've taken epi know the 2x2 table is the gift that keeps on giving in terms of measures of association and numbers we can crank out. There's only 4 cells in a 2x2 table, but the number of things we can compute based on them is infinite, it seems, sometimes. So let's talk about at least 2 more measures of association above and beyond the risk difference, something called the relative risk or risk ratio and something called the odds ratio. So again, we've been working with the risk difference, sometimes called the attributable risk, which is the difference in proportions. And of course, we've been working with this ad infinitum in the last 4 sections. But the sample from a study, the estimated risk difference, is just an observed difference in proportions. So example, in our AZT HIV transmission study, the risk difference in the AZT group compared to the placebo group in terms of the risk of infant contracting HIV is the 7% minus the 22% or negative 15%. And again, we've seen how to estimate this with the CSI command and get a confidence interval. How do we interpret this number, though? We've talked about it before, and I kept saying the difference in absolute proportions. But what does that really translate to in a public health context? Well, one way to think about this, that sample estimate of negative 15% AZT to placebo suggests that if we were, one way to contextualize this is to say if we gave AZT to a fixed number of people versus placebo, assuming causality, how many cases of HIV would we prevent? So, for example, we could say something like if AZT was given to 1,000 HIV-infected pregnant women, our study estimates that this would reduce the number of HIV-positive infants by 150 by that absolute decrease in 15% relative to the number we would see if these women were not treated. So it's kind of a good number to use to evaluate the public health impact of something, assuming causality, assuming the association is causal. If you gave this to a large number of people, this intervention, how many cases would you prevent in a population with a fixed size? How do we bring in uncertainty to this and cast it in the same light? Well, remember our confidence interval was from negative 22% to negative 7.5%. So one way to phrase this would be, additionally, our study results suggest that the reduction in HIV-positive births from 1,000 positive pregnant women treated with AZT could range from 75 to 220 fewer than the number occurring if these 1,000 women were not treated. So this really puts a face on the potential impact of this as an intervention in prenatal care for HIV-positive women. It says, wow, if you give this to a large number of women, you could actually stave off a large number of cases. But there's another measure of association which better estimates what the efficacy or association will be in any one woman given treatment versus not. And this is called the relative risk or risk ratio. It's the ratio of proportions. So in the AZT HIV study, our sample estimated relative risk is always given by our ratio of sample proportions, P1 hat over P2 hat. So example, in our HIV study, the risk of HIV with AZT relative to placebo, we'd estimate that to be that 7% over the 22%, a relative risk of 0.32. This is a number less than 1. It's a comparison of the risk on the top group to the bottom. One way to say this is that we estimate children whose mother is given AZT during pregnancy have 32% the risk of contracting HIV when compared to children whose mothers were untreated. Another way to say this and indicate clearly that there's a negative association, a reduction in the proportion in our study for AZT versus placebo, is to say the risk of HIV transmission with AZT is about 1/3 the risk of transmission with placebo. 0.32 is roughly 1/3. How do we get Stata to estimate this for us and give us a confidence interval? There's going to be uncertainty with this as well. Well, it turns out it's always been there. The CSI command, we didn't even touch what it can do for us. And there's a row right below where it says risk difference, where it gives us this risk ratio. And here it gives it at the 0.33. It's slightly different than mine because I rounded the proportions that I used. I had 0.32, but same order of magnitude, similar number. But it gives us, not only that, but it gives us a confidence interval for this. So how could we interpret the relative risk? Well, one way to qualify this in a sentence, at least our sample estimate of 0.32 or 0.33 would be to say something like an HIV-positive woman could reduce her personal risk of giving birth to an HIV-positive child by nearly 70% if she takes AZT during her pregnancy. How could we bring in the uncertainty? See if you can translate the confidence interval into something like this. Go back to it and see if this makes sense. The study results suggest that this reduction in risk could be as small as 40% and as large as 82%. Just FYI, just like the risk difference, it's arbitrary which direction we compute the relative risk. Here, it makes the study question easier to answer if we do AZT relative to placebo, because that's the direction of comparison of interest, but we don't have to do it that way. They're just numbers from two groups. And the relative risk could be computed in the other direction as well. If we computed the relative risk of transition from mother to infant for placebo compared to AZT, we just invert that relative risk we got in the other direction. We take 0.22 over 0.07, get a relative risk of 3.1. And here's, if we entered the numbers in the opposite direction with the CSI command, this is what we'd get. And here's some sentences interpreting that in context. So again, as with anything where we're comparing two numbers, the direction of comparison is somewhat arbitrary. Doesn't affect the results as long as you know who is being compared to who. Who's on the top and who's on the bottom. Doesn't change our story if we say those on the placebo were 3 times as likely to be infected as those on AZT versus those on AZT were 1/3 times as likely to be infected as those. Same story, just a different direction, but we want to make sure we know who's being compared to who with each numerical summary. What is the hypothesis of equal proportions expressed by the relative risk? I didn't say this yet, but think about that confidence interval for the relative risk. It didn't include a key number there, and let's try and figure out what the key number is. Well, here are 3 equivalent sets of hypotheses, and I'll just compare the null across the 3 to show you there are 3 ways of expressing the equality of proportions as a null. One is to say directly P1 equals P2. The population proportion of infants contracting HIV, mothers given AZT, and mothers given placebo are equal. Another way to say this null is that the difference, P1 minus P2, is 0. Another way to say the exact same thing is that P1 divided by P2 is 1. Each of these nulls is only true if the others are true and vice versa. They're all the same statement, the same hypothesis, quantified in different ways. So testing whether or not the proportions is equal is equivalent to testing whether the risk difference is 0, which is equivalent to testing that the relative risk is 1. However, these two quantities, the relative risk and the risk difference, give you 2 different pieces of a story, which we'll talk about a little bit more. The risk difference, or attributable risk, provides a measure of the public health impact of an exposure, assuming causality. How many cases will we prevent or incur extra with one treatment versus another in a group of fixed size? This is helpful for making public health planning decisions to large groups of people. The relative risk is more of a clinically useful number, provides a measure of the magnitude of these disease exposure association for an individual. Each provides a different piece of information about the story, and frequently only one of the 2 is reported, the one that sounds sexier. But let me just give you some examples. Again, in the AZT example, in this study, 22% of the untreated mothers gave birth to children with HIV. So think about this. If AZT reduces HIV transmission relative to doing nothing, i.e. placebo, what's the most our risk difference could be in terms of magnitude, or the least it could be numerically? Well, it can't get any smaller than negative 22%, correct? Because the best AZT could do in the sample study is we could have no cases in the AZT group. But our upper bound for how much we reduce it is the total percentage in the placebo group. So we can't go any lower than negative 22%. And as it turns out, our observed risk difference was negative 15%, and the relative risk was 0.32. However, suppose that only 2%, just hypothetically speaking, only 2% of the children born to untreated HIV-positive women became HIV positive. so that the baseline risk of transmission was a lot lower than it was in real life. This is hypothetical. Well, even if AZT were wiped out the possibility of HIV transmission altogether, the sexiest the risk difference could be is negative 2%, because we can't go any lower than reducing all the cases in the placebo group, and only 2% of the children in the placebo group became HIV positive. So the lowest our observed risk difference could be is negative 2%, which doesn't sound nearly as sexy as negative 15%. But that's because this transmission on the whole in this hypothetical example is a lot less of a risk than in the real life scenario we consider. So suppose the percentage in the AZT treated woman was 0.6% compared to the 2%. This would give us the same relative risk as we saw in the previous real life example of 0.32. However, the risk difference here is negative 1.4% versus negative 15%. So think about this. If you were to report the results of either study and only quote the relative risk and not the risk difference, the efficacy at the individual level is the same, but the potential public health impact is different because in the two scenarios, the underlying risk of transmission is different. So just think about that. On the flip side, suppose that 90% of the children born to untreated HIV-positive women became HIV positive. And suppose that this percentage was 75% for mothers taking AZT during pregnancy. Well, here again, the risk difference, AZT to placebo, is negative 15%, like we saw in the original study, but the relative risk is a lot less dramatic. It's 0.83. And that's because the overall risk of this is a lot higher than we saw in the original study. So even a great similar absolute decrease is proportionally not as striking. So what I'm trying to impart to you here, and then I posted something on the website going through more examples of this, just some stuff I found in the press, etc., is that unless both numbers are reported, it's not necessarily clear how to compare results between different sets of studies, because both of these are impacted by the background or untreated risk. One more measure of association that we'll define here for completeness purposes, but we'll pretty much then leave untouched until the second term, is something called the odds ratio. Like the relative risk, the odds ratio provides a measure of association in ratio format as opposed to a difference. Odds, what is odds? Odds is a function of risk or prevalence, or the proportion having outcome, but it's not the pure risk or the proportion. It's a function, as I said. It's the ratio of the risk of having an outcome to the risk of not having an outcome. So, for example, if P represents the proportion or risk of having an outcome, then the odds is given by P over 1 minus P. So in our HIV-AZT example, the estimated risk of giving birth to an HIV-infected child among mothers treated with AZT was 7%. The corresponding odds estimate is 7% divided by 1 minus 7%, or 0.07 divided by 0.93. The odds is close to the risk here. It's about 0.08. In the other group, the placebo group, the estimated risk of giving birth to an HIV-infected child among mothers not treated was 22%, or 0.22. And the corresponding odds of contracting HIV, children born to mothers in the placebo group, would be that 0.22 over 1 minus 0.22, which would give us an odds of 0.28, which is higher than the observed risk. The estimated odds ratio of an HIV birth with AZT relative to placebo would be the ratio of those two odds. It gets confusing because each of the odds is computed by taking a ratio, and then we take the ratio of those ratios. So an odds ratio is a ratio of two odds and implies the comparison. The odds ratio here was 0.08 divided by 0.28, or about 0.28. It comes in slightly lower than the observed relative risk of 0.32, but it's on a similar order of magnitude. How do we get this? The computer to do this for us? It's doing everything else for us, right? Well, from the CSI command, we can add the option OR, and it will add a line about the odds ratio. And you can see it here. The odds ratio estimate is 0.28, and it gives a confidence interval 0.14 to 0.54 by something called the cornfield method. And there's a couple different approaches to estimating a confidence interval. One famous one is by a statistician named Cornfield, and that's the method that's been used here. Notice that the confidence interval for the odds ratio does not include a key number. What would be the key number for an odds ratio? If the true underlying proportions were equal, what would the odds ratio be? I'll put that out as a question you can think about, but we'll explore shortly. So just to interpret, if we wanted to discuss the odds ratio, we could say AZT is associated with an estimated 72% reduction, one way to say this, in odds of giving birth to an HIV-infected child among HIV-infected pregnant women. Studies results suggest that this reduction in odds could be as small as 46% and as large as 86%. See if you can get that based on what the confidence interval was. What about a p-value? And what's the null value for an odds ratio anyway? I sort of put that out there 2 slides ago. Did you think about it? I'm sure you did, and you'll agree with my answer here. Well, think about it. If the true proportions are equal at the population level and there's no association between the grouping factor and the outcome, then what would the true odds ratio be? Well, it turns out if P1 equals P2, then the odds in both groups will be the same, and the odds ratio would be 1. So just like the relative risk, although it's a different number, the null value is also 1. So if we wanted to get a p-value for this, we're testing the null that the true odds ratio at the population level is 1 versus the alternative that it's not 1. But we know the only way the odds ratio would be 1 would be if the true underlying proportions are equal. And we already have a test for that, which is the same test we used whether we were comparing the risk difference to 0, the relative risk to 1, and now the odds ratio to 1. It's the chi-squared or Fisher's exact test. So even though that's why we always only get one line for the p-value, no matter how many measures of association we get cranked out by the CSI command. So that same p-value applies to every approach to measuring association for the null hypothesis. What you see on the screen here are 4 columns with 2 rows indicating 4 different ways of saying the same thing in the null and alternative. These are equivalent sets of hypotheses. That's why we need only one test, regardless of which measure of association we look at. How does the odds ratio compare to the relative risk? Well, it's never going to betray the results from relative risk. The odds ratio will always estimate the same direction of association. If the odds ratio estimate is less than 1, then the corresponding relative risk will be less than 1 in the sample, vice versa. And if the odds ratio observed is equal to 1, then the observed relative risk would be equal to 1. If the confidence interval for the odds ratio does not include 1, the confidence interval for the relative risk will not include 1. They will never give a different inference to the population level based on the confidence intervals. And if the confidence interval for the odds ratio does include 1, then the corresponding confidence interval for the relative risk will include 1. They're not necessarily numerically similar, however. However, the lower the underlying risk in both groups being compared is, the more similar the odds ratio and relative risk will be in magnitude. And we'll talk more about this and the utility of this fact in stat reasoning 2. So just to illustrate this, recall in our AZT example, 7% of the AZT-treated mothers and 22% of the untreated mothers gave birth to children with HIV. Relative risk was 0.32, odds ratio 0.28. Numerically similar, but not equivalent. Suppose that only 2% of the children born to untreated HIV-positive mothers became HIV positive. So we had lower underlying risk, hypothetically. And that the percentage in the AZT-treated woman was that 0.6% we talked about before. Well, here the relative risk is again 0.32, and the odds ratio is a little bit closer numerically. It's 0.30. However, suppose we had the opposite situation. Suppose that 90% of the children born untreated HIV-positive women became HIV positive, and this percentage was 75% for mothers taking the AZT treatment during pregnancy. Well, here the relative risk would be 0.83, but the odds ratio would be 0.33. Very different numerically. Both indicating the same direction of association. They're not going to betray each other, but they aren't necessarily always numerically equivalent. So you might be thinking, well, so what? Why even bother with this odds ratio? I just want to introduce it here, and then I'm going to blow it off until stat reasoning 2. Well, it is definitely less intuitively interpretable. It's not a direct comparison of risks. It's a direct comparison of a function of risks. However, we will see in stat reasoning 2 that with certain types of non-randomized study designs, we cannot get a valid estimate of relative risk. However, we can still get a valid estimate of the odds ratio, and that will be the only measure of association we can use to quantify the relationship between a binary outcome and a binary grouping factor.